Okay, welcome back. Dr. P here, and in this lecture we'll take a look at some more characteristics of SN1 reactions. Now, the one part that or actually one of the two areas that we did not get to in the last lecture was the nature of the substrate. And the whole point about the substrate is the substrate has to make a stable carbocation intermediate. So, for example, if we got the T-butyl carbocation here, this is stabilized by hyperconjugation. So think back to, we talked a little bit about carbocation stability back in chapter 7, so you can go back and look up hyperconjugation. We could also have something like the following carbocation, where we get resonance stabilization. Let me add in the hydrogens here, positive charge there. So if we want to look at speed of reaction, at the faster end, we'll have things like R3CBr, so our tertiary, which is going to be greater than secondary, which is going to be greater than primary, which is going to be greater than methyl. Let me write it like that. And then, because we can have resonance stabilization, we could have something like an allylic halide that would give the allylic carbocation, which is resonance stabilized. And even though it looks like it's primary, because that carbon has 2 hydrogens and just the one R group here, it's actually equivalent in stability to the secondary carbocation. And something like the benzyl halide would form a carbocation with about the same stability as a tertiary carbocation. And I know the text puts the benzyl with the allyl, but I've seen other texts where they have it with the tertiary. Notice this is the opposite order from what we saw with the SN2 reaction. So our SN1 reactions go faster with the more substituted substrates because they produce the more stable carbocation. And the reason for that is, if we look at our reaction diagram here, and if we had a more stable intermediate, what that means is that the energy required to get to the transition state is less. So now I've got a smaller activation energy than I did before. So a more stable carbocation means more stable intermediate. More stable intermediate means lower energy transition state. So that's going to speed up the reaction. Okay. Now, interestingly, there are some substrates, some alkyl halides that will, or I should say some halides, not necessarily alkyl, it could be benzyl or something like that, that actually have the ability to react fast in both SN2 and SN1. And you should think about which some of these might be. All right, so let's go ahead then and take a look at the stereochemistry. And the stereochemistry that we get here is what's called racemization. That is, we get a racemic mixture. So if we start out with OH, this guy here, so of course my hydrogen's back there, and I treat this with HCl, I'll protonate the OH, it will leave, and I will get a racemic mixture. So a mixture of both the R and the S enantiomers. And the reason for that is that our our intermediate is planar. So here's the T-butyl carbocation, and see how all the carbons are in the same plane? So this is planar. So now our I took apart my well, here we'll use the nitrogen here as a nucleophile. I took apart my cyanide. This guy can come in from either face of the carbocation, and one will give the R enantiomer and one will give the S enantiomer. So we get this racemization because it's due to the fact that our carbocation is planar. So if I was going to draw this intermediate here, I would have this as my carbocation, and then my Cl minus Cl minus can attack from the front or the back. So if my carbocation is in the plane of the paper, I could have a chlorine attacking from the front, coming in from the front, or it could come in from behind, from underneath the plane of the paper. So front or back, and you'll end up getting a mixture. Okay. I want to maybe end things with end the substitution discussion here with a summary. Okay, let's get that in there. That looks good. So we'll look at whatever characteristic we're looking at. And make this a nice big one here. And then we'll have SN1, and we'll have SN2. So when we're looking at kinetics, we have our SN1 is first order, and SN2 is second order. Extend these lines here, and I'll go ahead and write the next one in a different ink here, just so you got a little color to differentiate the lines here. Our rate determining step is unimolecular for SN1, and it's bimolecular for SN2. For the nucleophile, a weak nucleophile is OK for SN1, but we need a good nucleophile for SN2. All right, next was the leaving group, and in both cases we need a good leaving group. All right, let me continue this down here. All right, what was next? The substrate. So a tertiary will be faster than a secondary, would be faster than a primary. And I should say that's much faster than a primary. And really you're only going to get SN1 mostly with tertiary, could be secondary, or with an allyl or a benzyl. And you typically don't actually get it with primary, but I'll put that on there anyway. And we see the opposite reactivity in SN2. A methyl is faster than a primary, is faster than a secondary. So less hindered is faster with SN2. The more substituents we have, the more stable the carbocation, so those would be faster with SN1. For stereochemistry, for SN1, we just saw we get racemization. And for SN2, we get inversion. We also have the solvent. And for the solvent, we want solvent that is protic for SN1. And we want polar aprotic for SN2. And then lastly, we've got rearrangements. And since SN1 goes through a carbocation intermediate, these are somewhat common. These rearrangements are somewhat common. And we'll take a look at some examples of those in a future video. But with SN2, we never get rearrangements. Why? Well, we never form a carbocation, and it's the carbocation that will rearrange to form a more stable carbocation. So I think this is a pretty good summary, so you guys can jot this down. And then in the next lecture video, trying to think if I want to get into eliminations right away, or maybe I'll do a few examples of SN1 and SN2 reactions, and then we can go from there. All right. Well, until then, stay safe out there. Bye now.